and our applications. If we go through the history, so before going through the history, what is an observer? We must think about that, how we can use that observer, where we can use, and what can be the most potential applications of the observers. In the current scenario, we are working on microwave frequencies, and we are sneaking towards the terahertz frequency spectrum. And if we are talking about the terahertz spectrum, then definitely we have to talk about micro and nanoscale nanoscale devices. In fact, if we talk about application parts, so this becomes very urgent to understand the applications of the observers. Like observers are currently being utilized in medicine, in the sector of medicines, defense, and in our solar cell technologies, and many more related applications are there. Simplest application I would like to discuss about the stealth technology. Like I hope most of you understand about the stealth technology. Like if our aircraft is moving towards the radar of other country, then if we just want that they do not detect our aircraft, in that case we put our absorbing units on the top surface of our aircraft. And if that aircraft having coating of absorbing units at its top surface is moving towards the FOIS radar system, then definitely they will never be able to detect our aircraft. So this is the most potential application in the defense sector. In the similar manner, we can utilize the absorption-based devices in biosensing applications as well. So many more things are there that we will discuss in this session today. So if we go through the history of observers, so in 1860, Kirchhoff gives an idea of absorbing all the electromagnetic waves using a black body respective to wavelength, frequency, and angle of incidence. So what is happening exactly? The idea came from the Kirchhoff in 1860 that if suppose we are having a black body and any frequency spectrum of electromagnetic wave falls over that black body, then this whole spectrum must be absorbed and nothing will be reflected back. So Kirchhoff just gave an idea that this black body will particularly absorb all the spectrum. But after certain years, Planck just modified this concept of black body absorption, and some modifications were incorporated by Planck. And the modifications were like allow the black body must allow the radiation to enter but not reflect. That black body, what is being utilized as the absorbing unit, this may allow radiation to enter, but it should not reflect. No electromagnetic wave should be reflected back from the black body. So this was the first condition that was imposed by Planck over that physics that was given by Kirchhoff. And second condition was possess a minimum thickness adequate to absorb the incident radiation and prevent its re-emission. Like suppose we are talking about a black body which is being utilized at the main absorbing unit in particular device. So what will happen? There is another condition if that this black body must reflect, must have some specific thickness. And if we are going low to that thickness of the black body, then in that case, it will be difficult to absorb all the spectrum incidents on the black body. And the third condition imposed by Planck was satisfy that the black body must satisfy severe limitations upon scattering to prevent radiation from entering and bouncing back out. Like if you are talking about the black body, then and an electromagnetic spectrum falls over that black body, then it must prevent radiation from entry and bouncing back. Means any kind of radiation should not be allowed from that platform, that black body. And finally, the concept came that came in the concept resulted in many applications. Like if we talk about a simplest example, like if we are talking about cavity with hole, we can say we are having this cavity, and within this cavity, if we see here, an electromagnetic wave falls, enters in this black body. And in that case, what happens? There are the multiple reflections when this wave interacts with the inner surface or inner boundaries of this black body. Then what happens after multiple reflections from the inner surface? Those all the waves created superimposed to each other, and finally the whole energy is particularly absorbed. And you can check it out. There is no reflected back signal. This is the important thing. So this is the kind of black body that we can say here. Initially, this was not a concept like we can make a cavity with hole and we can trap some electromagnetic spectrum inside this cavity, and we do not let it go outside from this cavity. So this was a concept like simply we are having a body, whether this is hollow or anything solid, and it must absorb all the things. Finally, we had modified the structures. We had utilized the concept of resonances, and then we have utilized the concept of multiple reflections and destructive interferences. And then these whole concepts came together to form in the era of absorbers that we are currently utilizing in multiple applications right now. So here, if we are talking about absorbers, so this is very important to understand. This is a simple basic unit of absorber. You can see over here. Okay, and if you can see an electromagnetic wave falls over this absorber in this way, having some, well, this is a transverse electromagnetic wave, and this is having electric field or vectors oriented along the x-axis, and magnetic field vectors oriented along y-axis, and this is the direction of propagation along z. This is being represented by the wave vector kz. And when this electromagnetic wave falls over this absorber, then what happens? This complete spectrum must be absorbed. So we can say first condition imposed by that Planck, no reflected power should occur when this device is being particularly utilized as an absorber. Okay, and furthermore, if electromagnetic wave is falling over there in the direction of wave vector kz, then in the opposite direction, no transmitted wave should be there. So we can see here there is no transmitted wave. No transmitted wave. So first concept, no reflected wave, no transmitted wave. So in this case, whenever there is no transmitted wave and no reflected wave, then complete electromagnetic wave falling over this unit will be absorbed perfectly. Here, if we talk about the micro and nano scale devices specifically, in that case, you can consider like we must think these micro and nano scale devices work on the physical concept of localized surface plasmons mode, propagating surface plasmons mode, and Fabry-Perot resonance modes. We'll discuss about the physical concept behind the devices being utilized as an absorber. So here, simply, if we discuss the concept of frequency selective surfaces. So what is the concept of frequency selective surfaces? Simply, suppose we are working over a spectrum, and we are having a minimum reflection over a certain frequency spectrum. So we know the concept of frequency selective surfaces means this device is particularly being utilized at particular frequency only. So that's why this is being called as the frequency selective surface. In particular frequency range can be selected and can be absorbed, reflected, or transmitted depending upon the choice of the application. So here the basic concept is like if we if we just want to implement an absorber, then in that case we can see this is a single unit that we are seeing over here, and this is a plus shape of geometry, plus shape geometry, and this plus shape geometry or cross shape geometry, this is called resonator. Okay, and in between of that resonator there is one thing that is called spacer. Dielectric, this is made up of dielectric material most probably, and the back side is back reflecting plane. Back reflecting planes, these are basically made up of metallic materials, metals, okay, which shows the high conductivity, and that can those can be utilized as reflector for the incident electromagnetic wave. So what happens generally when electromagnetic wave falls over this absorbing unit? In that case, this resonator, this resonator, cross-shaped resonator kind of geometry creates some resonance. This gives some resonance spectra, and this provides us the minimum resonance at particular frequency or within particular frequency spectrum band. Okay, and just think, if we do one thing within this frequency spectrum, if we do some exercise like we stop transmission, reflection is already approximately zero in this particular frequency band f1 to f2. Now if we do one exercise like if we mitigate the transmission within this frequency range f1 and f2, we do some exercise like transmission becomes zero, or h21 parameter mod of h21 parameter square becomes zero. So in that case, this whole structure will be or can be utilized as an absorber. Okay, so this resonator unit, you know well, this already provides reflection zero, near about zero within a certain frequency range or spectrum. Now we have to do that transmission of zero. So what we will do, we will place some back reflecting plane at the back side, which is metallic plane, and this acts as the reflector. So when any electromagnetic wave falls over this unit, then this wave is reflected back, and then resonator is already providing the minimum reflection, so means no reflection is there, r is already zero, and due to this placement of this back reflecting plane, transmission becomes zero. So in that case, this whole unit will be utilized as an absorber. Okay, and so we'll do, if we try to understand the concept of absorption. So this is absorbing unit, absorbing unit, and here what we are doing, this is incident wave, and when it interacts with this absorbing unit S11, there should be some there may be some reflected wave, and there may be some transmitted wave. Okay, so what will happen if we establish a relationship between the impedance of this absorbing unit, impedance of this absorbing unit, and the scattering parameters. S11 is representing the reflection coefficient, S21 is representing the transmission coefficient. So in that case, this relation can be established over here, and you can find it with some mathematical exercise between the impedance and scattering parameters. And this is free space impedance, and this is having 377. Okay, so finally, just because of the placement of back reflecting plane, you can see S21 parameter, S21 means transmission parameter becomes 0. So we can remove this one from this mathematical expression. And here we find 1 plus S11 over 1 minus S11. So here this S11 also remains approximately 0. S11 also remains approximately 0. In that case, Z omega, you can see this will be equals to eta naught, means impedance offered by this absorbing unit will be approximately free space impedance. So this is called impedance match condition. So it totally depends upon the value of provided reflected wave. If this is 0, then impedance will be perfectly matched. If this is not 0, if means if this is near about 0, so this impedance offered by this absorbing unit will be near about eta naught. This is the basic concept. This is the first basic concept that we must understand. And that if we just trying to design some absorbing units, so in that case impedance, free space impedance should be matched with the impedance offered by absorbing unit, or absorb in the impedance of offered by absorbing unit must be matched to the free space impedance. Okay, so this is the first basic concept. And here finally, if we saw the overall concept of the absorption, then we can say absorption equals to 1 minus reflection coefficient minus transmission coefficient. If transmission is 0, transmission is 0, reflection is 0, in that case total absorption will be 1, and this is called the condition of perfect absorption. Perfect absorption. Okay, so generally this is very difficult to attain the value of a equals to 1, because approximately this we may completely block the transition, but it becomes very difficult to match this impedance offered by this absorbing unit perfectly to the free space impedance. There remains some negligible reflection, negligible amount of the reflected wave, and so that's why, and that may occur just because of material discontinuities or at the interface, or different kind of lossy materials available that we generally utilize in designing particular material. Okay, so here, so this is the first thing. Here, one thing I would like to discuss over here in this FTP. My motive of this presentation will cover this the benefits towards the research scholars who are just trying to who are just trying to start their work in the field of observers, and the people working in the field of observer as well. In fact, this lecture, today's session may be useful for undergraduate, postgraduate, and PhD scholars as well. So here we will discuss about the basic things about the observers, and we will go towards the advanced level, and then we will move towards the application part of the observer, and then we will also definitely discuss about the research gaps which are currently available in this research area. And that if we will discuss about the research gap, then definitely this will be very beneficial to the scholars working in this field. So here the first research gap you understood most probably, that we have to focus on the thing like how to attain the value of absorption near about perfect absorption, perfect level. How to attain the value of A equals to 1. So this is very important. So if somebody is working over here for attaining the value of absorption spectra equals to 1, then it will be very good thing, and they can move towards that in further way. Okay, so this was the all around the basic concept. This is the initial basic concept that we have to understand about the absorbing unit. And furthermore, if we had not discussed over this structure, basically this structure is made up of transmission line method. Transmission line method. This is equivalent circuit model, and This is made up of using physics behind transmission line method. This is not. There are two methods available in the theory. One is circuit theory approach, and another is transmission line methods. So generally, if we are working on the absorbing units, in that case, we will be utilizing the transmission line method. This is the most suitable method to prepare some equivalent circuit model for this absorbing units. So how we do this exercise, that we can prepare these uh, absorbers. You can understand over here. You can understand it over here. So here, first we should start from this metal plane. Okay. So if we are talking about the metal plane, and if we see the basic concept of the transmission line, so here we can use some transmission line, and we know this because this is the length of this transmission line. Okay, and this is source PS, and there is some current IS. Okay, and some internal circuitry will be there. You can understand RLGC, RL, and some GC. Fine. So this is the basic structure of the transmission line. And at the load end, ZL, this is ZL. Okay. So what we do, if we place the metallic plane at the back side, so this metallic plane will be utilized as the short circuited transmission line. So this is transmission line section, this is transmission line section having length T, and this transmission line section is short circuited at the load end. So ZL equals to 0. You can see over here this ZL equals to 0. So if ZL equals to 0, so simply what will be the value of input impedance? Z naught ZL minus ZZ naught tan beta L over Z naught JZL tan beta L. So if Z naught ZL equals to 0, in that case this becomes 0 and this part becomes 0. So Zn equals to, this becomes J Z naught tan beta L. So you can understand this input impedance just because of this. If we are, if initially if we are having this metallic plane, so you can think over it, this metallic plane will be offering the impedance that will be in terms of tangent. Okay, and this metallic impedance will be acting as the perfect reflector itself. Fine. So if we talk about the if we calculate the reflection coefficient according to the transmission line length L or T, it is being represented by T or L, whatever. Fine. So in that case, this will be working as a perfect reflector. And finally, there is some dielectric spacer. And suppose this is the thickness T or L of this dielectric spacer. So it will be represented by the transition line having thickness T or L, whatever.
Hello, sir.
Yes, yes.
So input impedance formula is ZL plus JZ naught tan beta L only, na, sir? Plus or minus, sir? Plus only, na?
It totally depends upon the direction of current. So you can consider whether plus or minus. It is not a matter.
Okay, sir.
Yes. So you can take it as per your mathematical calculation. Fine. So if there is a thickness T, so here if we are utilizing this dielectric spacer, okay, so in that case, what will happen? What will happen? This dielectric spacer will be acting as a transmission line, and this transmission line will be, if metallic plane is grown at another side of this dielectric spacer, in that case this transmission line will be acting as the short circuited transmission line. And then finally, so I hope you understood this section of this whole circuit. This section is clear. This transmission line, dielectric spacer is being utilized as a transmission line having thickness T or L, and if metallic plane is placed at the bottom, then this transmission line is short circuit. So simply, if we remove this metallic plane, then what will happen? This transmission line will be acting as the open circuit. Okay, or if we place some any resistive material that is offering resistance RL, so this will be terminated at resistance RL or anything. I hope you understood this concept. So now this part is still remaining. So this cross shape, already I told you, this cross shaped resonator. This is a resonator, and a resonator means, you understand this well, means this is providing some minimum reflection over certain frequency spectrum. And one more thing, if we are going through the concept of absorbing absorbing cells, then definitely this is blocking some transmission in the same frequency range. Okay, so in this frequency range transmission is also minimum. S21 is also 0 and S11 is also approximately 0. If there is no transition in this frequency band, so in that case we can say there is no transmission of the wave in this particular frequency spectrum. Okay, so in that case we can consider it as equivalent to the band stop filter in particular frequency spectrum. So if this is providing the band stop characteristics, then definitely we may deal with this resonator with the series RLC kind of circuit. Okay, and this series RLC circuit, you may deal with this in electrical circuit theory, like this provides the minimum current and maximum impedance, maximum impedance and minimum current at the resonant frequency. Okay, if we draw some impedance versus frequency plot of series RLC circuit, you will find minimum current at the resonant frequency and maximum peak of the impedance. Yes. So in that case, you will find this series RLC circuit, and this will be impedance offered by this total impedance offered by this whole circuitry can then be calculated. This circuit, this impedance, if this is a particular Z, you can represent it by, you can utilize your notation. And finally, this is the Z in, so we can make some equivalent circuit for this circuit analysis. So in that case, if this is ZR and already impedance offered by this whole section is Zin at this length of the transition line. So what will happen? This will be ZR and this will be Zin, and finally this is the characteristic impedance of free space that can be represented by Z, and total input impedance you can calculate in parallel. ZR parallel to Zin, Zin total. So this will be the total input impedance offered by this full absorbing unit cell. And in further way, this must be matched to at eta naught because S21 and S11 parameters are 0. So this is the basic concept and mathematical analysis. So we can prepare some equivalent electrical equivalent circuit model for this absorbing unit cell. And this is the basic concept behind this. So you may understand this physics in further way as well.
Sir, with what we have to match this impedance, sir? Zn parallel ZR?
We have to match this impedance with the free space impedance.
Free space impedance. Okay.
Yes, you see over here. Okay.
Yes. Okay, sir.
Okay. So this was the total mathematical and physical concept behind this absorbers. And if we see about this applications part, so now this is the time to discuss about the application part of this absorber. Like if you are working on the this gigahertz frequency spectrum, so in that case what will happen, so we can talk about the military applications. Already we had discussed over stealth application, automotive applications, telecommunications, antennas, EMC applications, RCS reductions. At the terahertz frequency, like we are simply gradually sneaking towards the terahertz frequency spectrum as well. So we can also talk about terahertz applications. These are so absorbing units are also having some potential applications at the terahertz spectrum as well, like in photovoltaics, shielding, photo detection, thermal imaging, thermal emission, and sensing. This is the most potential application in which absorbing units are currently being utilized at the terahertz frequency band, like in the cancerous cell detections, pesticide detections, and gas detections, air pollution detections, in COVID detections as well, influenza detection, and malaria and glucose. So many applications can happen whose some bacterial infections, influenza infections are there whose resonance frequencies, in fact cancerous tissues resonance frequency is around 1.63 to 1.65 terahertz. So we can also work over the detection of cancerous tissues in this frequency spectrum. Furthermore, if we see the optical spectrum, then this is having some potential applications like optical absorbers, carpets, and transparent sheets, or opaque transparent, non-transparent sheets, plasmonic sensors as well, like in terahertz frequency spectrum, biomedical applications like in terahertz frequency spectrum, and cancer detections, virus detections, all the infections, tissues, and viruses, bacteria are also having another frequencies, resonating frequencies at the optical spectrum as well. So we can also implement some optical devices, illusion sensor, insulin sensor, and blood group detection, absorption filters, and thermal imaging and emitting. This is another most potential application at the terahertz spectrum in which observers are being utilized, and switching, sensing, solar cell. And solar cell is the most hot applications in the current era that everyone is trying to work over it. In fact, our country is also investing so much amount on the development of solar cell technology. In fact, in 2021, there is a project of more than 200 crores that is being offered by Indian government right now. In fact, all the countries are trying to develop this solar cell technology all around, in which this solar cell absorber and the concept of absorber can be utilized at cost. Plasmonic sources. We will discuss about the things one by one. Like earlier, I was having some discussion over the microwave applications in the steel technology. Here, how the absorbing units are useful in steel technology, we can understand this easily. Like, suppose this is our aircraft. Okay, this is target, and this is radar. Okay, so the concept of radar everyone knows well since the graduation. Like, if this aircraft is moving in the direction of poised radar, in that case, what will happen? This radar signal using transmitter section transmits some red color signal. Okay, and that red color electromagnetic signal interacts with the outer surface of this aircraft, and some echoes are generated. Okay, and the green color signal. These are being called as echo signals. And then these echo signals are returning back towards that radar of voice. And using receiver section, the radar system receives that signal, and finally this signal is processed using matched filter and further devices, low noise amplifier, and furthermore devices. So in that case, we find using the Doppler effect, we can find a speed of this aircraft and distance from the radar system, uh, and related things, whatever the parameter we can just want to using Doppler effect. So this is the basic concept of radar system. Okay, so what will happen? The main problem which is happening just because of this created echoes, green color signal. So if our target is moving towards a Foy's radar system and we do not want let that radar system detect our target, we just want this thing like our target move towards that radar system of enemy, and we destroyed that particular location, and after destroying that location our target safely moves towards our country. So in that case what we'll do, we'll just put some absorbing unit of this on the top surface of this plane, and basically main signal echo signal which are reflected back is the antenna section mounted on this aircraft. So around the antenna section if we place heavy intensified absorbing units, so what will happen, these echo signal will never be generated. Means what will happen, the total incident electromagnetic spectrum which is coming from radar signal of voice enemy, it it will be completely absorbed at the top surfaces of this aircraft if absorbing cells are placed. And once this signal is perfectly absorbed, means no reflected wave will be there, means this enemy radar system will never be able to detect our target. We will hit the target, will hit this target and return back. Our aircraft will return back safely. So this is the concept of stealth technology that must be developed properly. For the development of this concept, and certain Indian organizations are working, like NAL, Bangalore, through DRDO, Tech Ahmedabad as well. So we can also work in that direction. We can also write some projects as well in this direction, so that we can develop some systems which can be useful in stealth technology. Next one is the sensing terahertz application. If we talk about terahertz applications, the sensing is the most prominent application in which the observers are currently being utilized. Like suppose this is an absorber, simple absorber. Okay, so what we do, at the absorber, at the top of the absorber, we place some analyte. Okay, and this analyte is basically tissue, infected tissue, influenza virus, blood cell, water with glucose, or anything, moisture in the air, or anything, or gaseous tissue, gas, methane gas, pesticide, or anything. Okay, so here, if we just suppose we are talking about, we just want to detect malaria in blood. Okay, so what we'll do, we'll take normal blood, we'll take normal blood, and we place this blood at the top of this absorber. Okay, and if we will detect the property, we know the refractive index of this absorber, and everything will know, and we'll find some resonant frequency, some absorption spectra somewhere here at this frequency. Okay, and now we'll place infected blood with malaria virus. So what will happen, due to presence of malaria virus, the refractive index of blood will be changed, and once this refractive index of blood will be changed, the absorption spectra of this absorbing unit will be shifted either in backside or in forward side. Okay, so if there is shift in the absorption spectra of this whole absorbing unit in from the case when we are just trying to detect the normal blood, so in that case you will understand there is some infection of malaria virus. Okay, and technically there are certain parameters which define the performance of this absorber. This is being, that can be called as biosensor. In that case, this absorber can be called as biosensor. Okay, so this biosensor, the performance of this biosensor can be uh, can be characterized in certain parameters like sensitivity. Okay, figure of merit, quality factor, and next one is FWHM, full width half maximum. So like if sensitivity means how much shift is there when we place some normal blood, and when we replace this normal blood with some infected blood, then this is large shift, means this absorber or biosensor is providing high sensitivity, and such biosensors are difficult to develop. So this is another research area, means we have to develop some absorbers or biosensors which can provide high sensitivity or ultra high sensitivity. Means in fact a small change in the refractive index 1.001 change can be detected with the large amount of shift in this absorption spectra. So this will be very beneficial to develop such kind of absorbing units. So you can also work in this direction to develop such kind of absorbers who can provide the high sensitivity. Figure of merit, this is approximately 1 upon s. This is some relative quantity. If sensitivity is higher, then particularly we can count the figure of merit. So quality factor. Quality factor means this defines the peak frequency over FWHM. FWHM means, if suppose this is maximum value and this is 50% value. So how much is the bandwidth at 50% of this absorption? So this is called FWHM. Quality factor will be high if peak frequency will be nearly 1, or if FWHM is minimum. Okay, if this is narrow. So this is if any absorber or biosensor is able to provide narrowest band, then it will provide quality factor which will be very high, and high quality factor, it will somehow provide ultra high sensitivity as well. So this is another research gap, then someone can work toward that, the development of some biosensors having high sensitivity and ultra high Q factors as well. And narrow or ultra narrow spectrum means narrow FWHM. Okay, so we will discuss these all the research gap in detail as well. And if we are talking about the optical applications, so this is another most important application that we must utilize. We are currently trying to develop. In the case of solar cell, this is the thin film solar cell specifically, not chemical based solar cell. In the thin film solar cell, we can talk about this is simple structure I am just telling over here. This is back metal, back reflecting plane. This is silicon. Yeah, this is made up of, this is main absorbing geometry. Main absorbing geometry. Okay, absorbing geometry means this is the main structure which is utilized to confine the incident electromagnetic spectrum on this absorbing unit. Okay, and at the top we can provide some resonating structure like in absorber. So you can see this is the concept of absorber only in the solar cell. At the back side, this is back reflecting plane, then spacer, and then resonating unit. In simple case, like here till here, main unit, absorbing unit, and back reflecting plane. This is still called as the solar cell because silicon also can have the property of absorbing the incident optical electromagnetic spectrum. We can intensify this incident electromagnetic spectrum if we place some resonating unit at the top of the silicon. In the basic unit of solar cell, at the top surface, we provide some anti-reflection coating. Anti-reflection coating. This is in current days, generally we are utilizing indium tin oxide, ITO, for this, which is being utilized as anti-reflection coating or ARC. So you can see over here, like this is simple ARC means this silicon and back reflecting plane. This was providing the black color absorption spectra, and if we place some blue color, this resonating unit at the top of this absorb basic solar cell structure. In that case, this absorption is particularly enhanced, and this achieves a level of perfect absorption. If there is a perfect absorption at this frequency, and this is visible range of optical spectrum. This is the main spectrum, mainstream of the optical spectrum in which any solar cell can grab the maximum amount of incident solar energy. Okay, so this is another most hot applications in which you can implement some new research work. This is thin film solar cell, which the field of observers is being utilized. So these are some certain applications in which we are utilizing solar cells. Now, we can further discuss over the current research work which is going over all around the globe. And we should discuss about that. This is a very interesting section. We generally, this is my classification. If we are going to design some observers, so we generally classify these absorbing units in different parts. First one is a metallic absorber, metal based absorber. Second one, metal free absorbers or dielectric absorbers. Okay, and third one is semiconductor based absorbers. This is the categorization of absorbing units based on materials being utilized in the implementation of particular absorber. Okay, so if first we are talking about the metallic absorbers, this is simple. A metal backplane will be there, a spacer, air or some dielectric, and then resonating resistive sheet. This will be the incident electromagnetic wave. And furthermore, we can stack some layers of that resisting sheet as well. Spacer, then the resonating unit, spacer, then resonating unit, spacer, then resonating unit. Like if we want, suppose, okay, why we are utilizing this layered structure? Let me tell you in detail. Suppose we are utilizing this solar cell. This is, you can say, more than 80% or 90%. This absorber is providing maximum absorption within this frequency spectrum only. Suppose you do one exercise, like this is your complete visible spectrum, 400 to 700 nanometer, and you find characteristics like that. %90. All around absorption spectra covers the whole visual spectrum, having a with value of absorption coefficient more than 90%. And what will happen? The efficiency of the solar cell will be drastically increased. Right now, we are struggling, in fact, to achieve the efficiency of solar cell around 30% or more than 30% or more than 25% itself. In that case, if we are able to distrap whole optical spectrum in particular absorbing unit perfectly throughout the optical visible spectrum and beyond the visible spectrum itself, in that case what will happen, the efficiency of the implemented solar cell will be drastically enhanced. So this is the most beautiful thing that we can do by using some layered architecture. Like this resonator provides some spectrum peak here, and this resonator provides peak here. Then these peaks can be merged and we can find a complete spectrum of over a broad band. So this is one thing that we can do for utilizing multiple layers. The simplest example at the back metallic plane and then resonator. And in the case of metallic observer, if we discuss from the point of research gaps and research issues, generally metal made resonators, okay, which remains the main component and which are the main factor for the absorption of signal. What is the limitation that we are currently facing with the metallic components? Although these metallic components is difficult to remove from the point of fabrication and find from the point of compatibility with the different tiny systems or small scale systems in that case, but still, if we talk about metallic part at the terahertz frequency, the conductivity of metal reduces, because you know well, conductivity, permittivity, permeability, these are frequency dependent quantities, and at optical frequencies, whenever plasmonic reactions occur, in that case this conductivity can be defined using Drude's model. And if we are talking about Drude's model, so this is another way of showing the frequency dependence characteristics in the case of metallic geometries, metallic materials. So in that case, so at the higher frequencies, specifically starting from millimeter wave to some terahertz and optical range, the conductivity of normal metal reduces, like copper and aluminum. But if but if we are utilizing some novel metals like gold, silver, then conductivity somehow may retain. But problem with the uses of gold and silver, you can understand the problem with associated with the gold and silver. The cost, application cost is very high, and the cost of this materials is very high. So ultimately, if we just replace these metals by some other materials which are available, easily available in the nature, and which are available with low cost, in that case, if we make some our absorbing units, then it will be very beneficial. So this is one of the research gap you can understand over here. And another point, this is temperature sensitivity. So, you know, the characteristics of metals is highly temperature sensitive. So this is another problem that we can think over it. Means temperature breakdown may occur as much fast as possible in the case of metals. Another problem that is also being suffered by the metals is oxidization problem. Okay, so what is that oxidization? Here in air, in whenever we use some metals, like in the lower frequencies, or some metals like ferrous, iron, some corrosion occurs when it comes in the contact of air and moisture. And in the case of some noble metals, gold and silver, these are oxidized at the high frequency. If these come in the contact of air and moisture, then these are oxidized. This is the main problem. So what will happen after a certain time? This will reduce the reliability of the devices fabricated. In fact, the maintenance of the implemented or developed system um, developed system by utilizing the gold and silver or some other materials, metallic parts, it will be very difficult. Although things are going on, and technology is being developed slowly. Second one is semiconductor based absorbers. You can think over it, over semiconductor based absorbers as well. So what will happen in the case of semiconductor based absorbers? Here you can see some new compound materials are there, like in this indium antimony, silicon carbide. Some other things are also there. At the backside, metallic reflector and the spacer. In the place of spacer, we are trying to utilize some semiconductor kind of materials. So you can say some problems are also existing with semiconductor materials. Problems are like maintaining the purity of semiconductor material is not as an easy task. In fact, fabrication of semiconductor material is also not an easy task. And but here, the advantage of utilizing semiconductor-based materials is that they can provide high conductivity in comparison to dielectric materials. So in fact, we can mold the conductivity in terms during the fabrication process, manufacturing process. That thickness is significantly smaller in comparison to dielectric materials based absorbers or dielectric material based spacers. being utilized in the absorbing units. Furthermore, we can categorize the absorbers in the case of metal-free or dielectric structures. So generally, this is uh, some, you can say some structures are over here. This is spacer, blue color part is representing some spacer, dielectric spacer, and at the back side this is graphite. This is non-metallic material and but provides high conductivity. Okay, non-metallic but provides very high conductivity. It means the properties of the conducting material can be engraved if we are going to utilize graphite, and if we are trying to replace the metals from the graphite. So in that case, this is layered kind of structure: spacer, 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 some resonating unit is spacer, resonating unit is spacer, resonating unit is spacer, then resonating unit. At the top, this is graphene. This is 2D layered architecture of graphite, single layer most probably 0.34 nanometer thickness, and this is made up of, this is extracted from graphite generally. So four layers of graphites, four layers of spacer, and one layer of graphene. So this is totally metal-free structure. Okay, so this is totally metal-free structure, and here, if we see incident electromagnetic wave, this is completely absorbed. No transmitted wave, transmission is zero, no reflected wave. Finally, at the bottom, this is Rg. This is offering this back reflecting plane offers some resistance Rg. This is approximately equals to 0 ohm. And similar concept is being utilized over here. And this is another kind of geometry. This is, you can see over here, this is some dielectric made TiO2 kind of thing, titanium oxide, dielectric kind of structure, silicon or some other gallium arsenide as well, and some dielectric, thin dielectric spacer, and at bottom. So if we take high thickness of this dielectric material with high permittivity, then what will happen? No metallic reflector plane is required, and total transmission will be blocked, and reflection is completely blocked because this unit will be utilized as self-resonating structure as well. So limitation of these dielectric based units are these can provide large thickness in comparison to metal based or some other material based absorbers. So this is the limitation, but advantage you can understand, since these are made up of dielectric materials, so temperature sensitivity will be improved, will be higher in comparison to metal or other material based structures, and some other properties will also be considered in terms of dielectrics, like oxidization problem will not be there, not occur easily. Only the problem is thickness. So due to thickness, they may not be compatible with some future nanoscale systems in most of the applications. But still, the research is going on. Everything is like, so here you can understand. So if we again discuss about the physical concept from the starting, here you understand the research gap. In the case of metal-based absorber, you have to remove the metals. This is one research gap. Here in semiconductor waste, how to maintain the purity of materials, we can utilize or we can search some semiconductor materials which can provide the facilities, which can provide the more fabrication tolerances. In fact, the variation in the conductivity or materialistic characteristics of semiconductor materials cannot change the spectral behavior of the device. Okay, and next one is how to remove the thickness of dielectric based absorber. This is another research gap. Fine. So these are the research gaps which are these are the research areas in which the researchers around the globe are working hard to develop the technology that can be utilized in the future as well. In fact, this structure was fabricated by this author group, you can see, and you can go through this research article. And this was also utilized in terahertz imaging system as well. Okay. Furthermore, if we discuss about the research gap, so how to one research gap you understood in the case of solar cell, we we how to develop the broadband or ultra wideband absorbers. One more thing we had, I just forgot to discuss about the basic use of absorbers at the gigahertz frequency. You understood the in stealth technology. One more thing everyone knows perfectly, that is anechoic chambers. Anechoic chambers. Anechoic chambers. Okay, and terahertz, not terahertz only, EMI shieldings as well. EMI shieldings. Do you understand the concept of EMI shielding? This is like Steel's technology as well. Electromagnetic interference shielding. I hope, let me show you uh, this one. I hope you know this kind of this image at the center, this image. I hope you have seen this kind of image. A lot of conical triangular structures are there. These are made up of spoons, and at the back there's some metallic plane, metallic geometry. Some other things are also there, and some rooms are there in which antenna measurement is generally take place. We generally do antenna measurement or some other microwave or other fabricated devices measurement. So if we just want to make some electromagnetic interference free chambers or rooms, in that case absorber, these are absorbers. Okay, most commonly you have seen many times absorbers in your life if you are working in the field of electromagnetic. Fine. So this is the most hot applications at the lower frequencies right now we are working. In the similar manner, we can utilize these, we can implement the absorbers in terahertz electromagnetic shielding as well. Okay, terahertz electromagnetic shielding. So broadband shielding means, suppose we are working from for 0.1 to 20 terahertz around. We are trying to develop some wireless systems for approximately 10 terahertz, zero point 0.1 to 10 terahertz. So here definitely we'll have to develop the system that can provide the electromagnetic shielding. Shielding means the geometry which does not let pass the electromagnetic signal from one to another direction. In fact, no reflection is there. Okay, it means in the case of shielding we need some perfect absorption kind of thing throughout the band. Absorption equals to around 1, more than 90% throughout the frequency band. So this is ultra broadband spectrum, and this is shielding, broadband in microwave shielding, electromagnetic terahertz shielding, and optical shielding. Means no electromagnetic signal will be passing through this device and reflected back. So this is the uses of broadband, ultra wideband absorbers that we can do. Narrowband, ultra narrowband absorbers, you can understand already, you know this. These can be utilized in the sensors, we had discussed over it. Ultra sensitive, again these can be utilized in sensors with good high refractor performance indices. Multiband, multiband you know well, like suppose influenza H1N1 frequency is 1.41 terahertz, and cancerous tissues reflect some frequency 1.65 terahertz. Okay, and if we develop the single device which can provide one peak at 1.41 terahertz, another peak at 1.65 terahertz of absorption spectrum. So in that case, what will happen? This single device can be utilized as influenza sensor as well as cancerous tissue sensors. Okay, we does not need to fabricate or design or develop two different devices, one for cancer, one for influenza. Single device can be utilized. So that's why we need multi-band absorbers kind of. Reconfigurable. This is another important thing. This is very important thing currently that we are developing the systems with the characteristics of reconfigurability, specifically at the terahertz and optical frequencies. Terahertz and optical frequencies, we are trying to develop reconfigurable devices. In fact, at the gigahertz frequency, we are also trying to develop some reconfigurable devices. Like suppose we are having absorption spectrum at 1.41 terahertz, and somehow this we can, this is frequency spectrum, this is absorption, and at 1.65 terahertz this is cancer status. We had developed single band device, and just we just want to shift the absorption spectrum at 1.65 terahertz. So what will happen, this is called reconfiguration of this device. Means we had implemented single band device, and we are able to tune that frequency spectrum of this device to have from influenza to cancerous tissue frequency as well. So this is called reconfigurations. At the terahertz frequency, we are using graphene for reconfiguration. And you know, I would like to discuss the property of graphene in short. This provides some surface conductivity, and using Pure's formulas, this surface conductivity is a function of chemical potential of graphene. Chemical potential of graphene. Okay, means, and chemical potential of graphene is a function of applied electrostatic bias. Means suppose we are having a sheet of graphene, and if we apply some DC supply, DC battery, DC voltage, okay, DC voltage on this graphene sheet, then what will happen, its chemical potential will vary, and once we are able to vary the chemical potential, its surface conductivity will vary. And since surface conductivity already I discussed using Drude's model at the terahertz frequency, the surface conductivity is a function of frequency. If we are able to vary the surface conductivity, we will be able to vary the frequency of this device. Means we can change the frequency of operation of this spectrum. This graphene is the simplest material that is being utilized at the terahertz and optical frequency for reconfiguration purpose. And this is a big research gap in itself, how to develop the reconfigurable devices right now. So one can also work in this field, how to develop the reconfigurable absorbers, single band, dual band, multi-band, triple band, so, and broadband. Okay, polarization insensitive. What is the meaning of polarization? And a wide incidence angle. Okay, what is the meaning of polarization insensitive thing? So broadband spectrum, you understood. We need to develop such system which is having broadband approaches. Already you have understood how to reduce this FWHM, how to find out the ultra narrow absorbers, so that we can utilize in sensors, ultra sensitive as well, how to develop some structures which are ultra sensitive. This is one structure that was developed with the ultra sensitive characteristics by this author group and recently reported in IEEE sensor journals. And here it means if we change the analyte medium, refractive index of analyte medium at a small scale, this was providing ultra sensitivity of more than 111 terahertz. In fact, multi-band absorbers, you understood already, we had discussed multiple peaks are there in particular spectrum. And reconfigurable absorbers, you understood graphene. At the gigahertz frequency, we generally utilize varactor diodes, twin diodes, and other things. So many things are there that we can utilize for reconfiguration purpose. But at terahertz and optical frequency, we utilize some graphene kind of material. So here you can see we are applying some voltage and frequency spectrum is being changed. You can see frequency spectrum is moving to upward from this to this frequency. If we change the chemical potential of graphene, so frequency spectrum peak, this is the peak of frequency spectrum, and this frequency spectrum is moving, this is around 2.25, now this is around 2.5 here. So this is the tunability. And ultra thin, we can utilize semiconductor materials as well. Ultra thin, this is another research issue. How to develop this absorbing units with ultra thin geometries. For the future nanoscale systems, we need to develop some ultra thin geometry. In fact, in steels technology, if we are able to develop ultra thin absorbing cells, then it will be very easy to mount those absorbing cells at the top surface of aircraft, because it will not provide some extra burden or extra weight on the top surface of absorbing this aircraft as well. I hope you understood the meaning, the use of ultra thin absorbers as well from the example of aircraft or steel technology. Polarization intensity. So there are two types of polarization. Generally, we talk about TE polarization and TM polarization in electromagnetics. So one can go through the polarization of waves. Whenever electromagnetic wave incidence at the normal incidence or at the oblique incidence, the two polarization can be there, TE and TM, transverse electric polarization and transverse magnetic polarization. So if wave incidence with the trans TE polarization or TM polarization or any polarization, if Hy is in this direction and Ex there, and if an Ex is transverse or Hy is transverse, in both the cases or any cases, the response of device remains unchanged. In that case, this device is called as polarization insensitive. So here we can see, if in generalized case, if we talk about the spherical coordinate system, and if we see this phi angle, and here if this is Ex and here this is Hy, so with the variation of phi, if, or we can set the field vectors of the incident electromagnetic waves or at any particular angle of phi, particular value of phi, 0 to 362 pi. In that case, the variation in phi does not change the spectral behavior of the absorbing unit. So in that case, this is called polarization insensitive device. Okay. And furthermore, like one more beautiful example is there, how we can develop the polarization in sensitive devices. This is very easy to understand. Like you can see this geometry. This geometry is having some length. Suppose this is x-axis and this is y-axis. Okay, so what will happen? Uh, Along x-axis, dimension of this unit cell is more, L1. Along y-axis, this is L2, and L1 is greater than L2. In fact, the resonator size is different in x-axis and y-axis. So this unit cell will be providing some different effect for Ex and different effect for Hy. Means this will be differently affecting the incident electromagnetic waves component Ex and Hy. But here in this cell, you can see in this cell, you see this along x and y, both the length and dimensions are same. It means this absorbing unit will be affecting the incident electromagnetic waves equally along x and y on E and H vectors. So this second case will be polarization insensitive, but first case will be polarization sensitive. Okay, so generally this is another research gap, that we have to develop the polarization insensitive absorbers. Wide angle incidence. Already from the starting, I had discussed over that concept that in perfect black body, the incident electromagnetic wave was it was perfectly absorbing the incident electromagnetic wave irrespective to frequency, angle of incidence, and polarization of the incident electromagnetic wave. So we have to make the absorbing units in such a way that it does not affect the angle of incidence, means the spectral behavior of absorbing unit should not be affected by the incident electromagnetic angle of incidence of the incident electromagnetic wave. Means if you are working in the field, if you are the scholar of the electromagnetic field in the core and the language of core electromagnetics, let me tell you, if incident electromagnetic wave is coming on the particular medium at the interface with some normal incidence, whether at normal incidence theta equals to 90 degree or at some oblique incidence at particular value of theta, if its spectral behavior should not be changed. Okay, so here such absorbing units are there, like this is providing the similar kind of absorption over a broad frequency spectrum around the value of theta around 70 degree, and we have to increase this up to 90 degree. So this is another research gap. Okay, so here this theta elevation angle in the spherical coordinate system can define the incidence angle. The people working in the field of electromagnetic can understand. Okay, so this was all around the concept of absorbers, which was, and this is the concept of, these are the different research gaps which are available in the literature as well. Now I will discuss about the implementation. We had published very intensified several articles. One research article we had published in uh, uh, IEEE Sensor Journals in last 2020. This is on broadband spectrum absorption, and this was also being utilized as sensor as well. And the concept you can understand. This was the simple concept, and you can go through this research paper if you just want to study this work. And definitely this is metal free. This is made up of graphite dielectric spacer. This was recognized by IEEE Sensor Journal. You can go through this research work. You can find the whole concept of broadband absorbers as well. And there is another research work that we had carried out recently, uh, and this was the most emphatic research work that one researcher can understand in this publisher. This was published in Royal Society of Chemistry. This is most reputed research publication. This was published in Nanoscale group of articles. And here, this is bipolar charge trapping for absorption enhancement in a graphene-based ultra-thin dual-band terahertz biosensor. Here we had developed some graphene-based absorber, dual-band absorber, which was being utilized in malaria detection and glucose detection in water, malaria detection of blood and glucose detection in water, and some specific physics was used to enhance the absorption. Here you can see there are two structures. One structure without circular slot on this is black color is graphene sheet. So one graphene sheet without this annular circular slot. Another structure is with graphene, this annular slot. So you can see the red color absorption spectra. This provides dual band spectrum, but at top you can see in the upper band this absorption is around 50%. So here if we place some annular geometry in graphene, we just do some patternization of this graphene sheet. In that case, this absorption enhances to 100%. It becomes to the form of blue color plot. And that was just because of some specific reason, physics available. And it was like, if we do not place annular geometry at the center, then this generated surface plasmons at the graphene ear interface was having some mode index 1, and at the bottom in the dielectric graphene interface this was mode index 3 half wave variation, single half wave variation. So this was the reason behind that we were getting the 50% absorption in the upper band at the frequency of higher order mode. But at the frequency of, if in the similar frequency if we place some annular geometry, what will happen due to the placement of this annular geometry, this will provide the capacitive effect, and this will trap the charge along the direction of electric field vector. And here you can see this will trap like positive charge and negative charge, and just because of trapping of charge, this mode index here it was 1 and it becomes 3. And just because of equalization of mode index at either side of the graphene interface, either in air or dielectric, this absorption is enhanced to 100%, 99%. And furthermore, this is the physics behind, this is the beauty behind this whole research group, research article. You can just go through this research article, you will find definitely a piece on the name of research work in the field of absorbers. In fact, if we are utilizing graphene, then definitely already we had discussed utilizing graphene can provide us the tunability. So you can see this is the peak frequency. Red color is showing the peak frequency of absorption spectrum, and this peak frequency is shifting from 4 to 6 in the lower band and then 8 to 12 in the upper band when we are changing the chemical potential of graphene. Okay, and our next article was recently published in this August 2021 only in IEEE Transactions on Nanobioscience. And this was on altering the multimodal resonance in ultra-thin silicon ring for tunable terahertz IO sensing. This was published by my first research scholar, Mohammad Salman Khan, and by some research colleague. And here we can see this is silicon disk, ultra thin. So you can see another research gap, ultra thin. You understood the research gap. You can correlate that we had discussed earlier. And here some dipolar arrangement was being, this is also dual band response that we were obtaining. In the lower band, we were obtaining the magnetic dipole, resonance due to magnetic dipole. In the upper band, we were obtaining the resonance due to electric dipole. When we place a graphene ring in the center of this silicon ring, so what we do, we are again able to do some charge trapping kind of physics, and then we are able to tune the frequency of these absorption spectrum. Means we can separately tune the frequency of magnetic dipole, we can separately tune the frequency of electric dipole as well. And this is, you can see before placing the graphene seed, this green color spectrum was the electric field in the absorber, and after placing the graphene seed, we got this charge trapping, electric field enhancement, and this is just because of trapping of the charges. You can also go through this article. This is very beautiful physics behind it. You can understand. You will feel good if you will go through this research article. Next one we had recently published in this Journal of Optical Society of America B. This was multi-layered structure, and this was already having aiming the broadband absorbers, metal-free broadband absorber. Research gap, metal-free, wideband, broadband, another research gap. Multiband itself, multiband and metal free. Okay, so two research gaps, and we had published this in plasmonics. So we were able to get some multiband kind of geometry in multiple by engraving some multiple slots, geometrical changes. Okay, thank you everyone for joining this session. If there is any query, please you can discuss over here.
Participants, if you have any query, you can ask.
Sir, is this your work based on fabricated devices, or you have used computer simulations?
Right now, I'm working on fabrication as well. We are working on optical frequency fabrication. We had some collaboration with some foreign collaborators, and right now we are working in India as well with the fabrication technology. But currently, we publish these research work on the basis of simulation and an analytical approach only.
Okay. So, which simulators are available for this kind of work?
We can utilize two simulation tools. One is HFSS, another one is CST Microwave Studio. Okay, and in fact, if we go through the CST Microwave Studio, it remains a little bit easy to simulate the structures.
Okay. 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 Thank you.
Thank you.
Thank you, Gaurav sir, for nice explanation.
Yes, thank you, sir. Thank you, sir.
Thank you, sir. So participant, next session will be from 2:30, next technical session. So again, you join at 2:30, and attendance link is shared in chat box, so you can give the attendance. Thank you, sir. Thank you again.
Thank you, sir.
Thank you,
Okay.
sir.